Hey guys, so let me kind of explain to you what I'm trying to do with my motor controller that I want to build. Excuse me if I start sneezing, my allergies are acting up right now. And I'm also drinking some yummy Belgian white. This is not paid advertisement though. That works. Product placement, huh? Anyways, so yeah, so here's a couple of things that, as of right now, I've thought that I want in my my motor controller, and I've set something up here which I'm gonna start running in just a second, and then I'll show you what that looks like on the scope. I want my motor controller obviously to be remote controlled with a transmitter receiver pair, and that's these guys right here. And the cool thing is that when you buy these are relatively cheap. This came with a drone that I crashed into a lake and I lost it, but I still have this thing. This one I bought and it's relatively cheap, and they come with their own receivers, so you know it's not like you have to build that or anything, so that's cool. Now the thing about radio, the receivers and those transmitters, is they're kind of meant for servos and things like that. So the signal that you get from those is not going to be, for example, when you press this all the way up or all the way down, all that does, it varies the signal from, I think it's from 1 millisecond to 2 milliseconds. That's the whole variation. This entire thing will vary from 1 millisecond to 2 milliseconds. It might be 2.5, whatever. The point is you're not getting like an entire range of PWM. So in software, I have to map this 1 millisecond to 2 millisecond signal. I have to map that from 0 to 100% on my PW. Holy shit, I'm not even showing anything. So I have to map this 1 millisecond to 2 millisecond signal. I have to map it from 0 to 100. PWM duty cycle, and that's all done in software, so that's not a problem. Obviously another thing I want in my my motor controller is I want to use all N channel FETs, because that's going to offer much better efficiency, because N channel FETs tend to have a lower RDS on. But then that also comes with its own issues, because I have to use a bootstrap circuit, you know, obviously, so it's more circuitry. I have to use a special kind of driver for my high side MOSFETs. Another thing I would like is regenerative braking. What this means, I'm not even exactly 100% sure how I'm going to do this. I don't know how this works yet, but I'll figure it out. I think what this basically means is that when you're braking, it takes that energy and sends it back to the battery. So it's like every time you brake, you inadvertently are charging your battery, right? Even if it's, you know, a fraction of a second or whatever, you still, you know, that power isn't being lost. You're actually putting it back into the battery. I think that's what it means. And obviously I want it to be excuse me, optically isolated. And by that is that I want the actual MOSFETs and all the high voltage stuff to be isolated from the microcontroller and the receiver, just in case anything should get all fried up in there. So let me draw up this circuit that I have here, and in conjunction with the microcontroller, and I can show you guys what I have here, and then I'll show you guys on the scope what it looks like. Okay, shoot, let me move this. Let me take another sip. Alright, I have, so I have 4 MOSFETs. And even though I want all N-channel FETs, at the moment I am using P-channel FETs, because obviously what I want is a little complex as far as circuitry goes. So I want to start kind of simple, and then just take parts out and then replace them with what I really want, and just build the system up instead of trying to start with the most complex version of it. So these are P channel FETs. Oops, this is an N channel and this is an N channel. NN PP. In the middle is my motor, and you have your basic H bridge configuration. Right, here's ground. Here I have 12 volts. Then you obviously have your diodes here. And then this one is tied up to 12 volts. The gate of this P channel is tied up to 12 volts. The gate of this one is grounded, and the gate of this one is grounded. This one is being pulse width, I'll show it like that, pulse width modulated through an IC MOSFET driver. It's a what is this? 1407. It's a 1407. And what that does is this is going up to 12 volts and it's going to ground, and it's taking in a signal from my STM32, right? Oops, 32. And the STM32 is giving it a PWM signal, and it's matching it, except this signal here is from 0 to 3.3 volts, right? But then it's taking this signal and driving it up to 12 volts. So it's a 12 volt PWM that is going into that MOSFET. And then what I have here is an ADC channel, and I have a I'm not sure how I'll show this, a potentiometer, which is obviously just acting like a voltage divider. Oops, 3.3 volts. And then this potentiometer is just giving a signal to the ADC, and this is from 0 to I think 4095, I believe. And then my PWM resolution I have from 0 to 1000. So in software, what I'm doing is I'm turning this, and as this turns, the duty cycle of my PWM signal here is varying from 0 to 1000, basically percent, I guess. And then it's this thing is outputting that, and there you go. Now, since this one is high, that means it's off, and since this one is low, that means it's off. So my current path effectively is going from here to here, through my motor, and then down. And basically when that's happening, what you have here is a more positive potential here, right, and a negative potential over here, because the voltage is dropping, let's say, across the motor. And these diodes are the characteristic diodes of the MOSFET. They're not physical diodes in my circuit. These are the diodes that are inherently there in the MOSFETs. So what happens is when I turn this, so when this PWM signal is high, this MOSFET turns on, and the current is flowing through here, right? So you have a more positive voltage here, a more negative voltage here, and this is coming to ground. When you turn this signal off, so this MOSFET turns off. Now this is essentially, you can think of it as a coil. So what's going to happen is going to try to keep that potential, and what ends up happening is you get a reverse voltage spike here. Now that reverse voltage spike is going to be in this opposite polarity, so it's going to be positive on this side, negative on this side, and that big positive spike of voltage is going to damage my my MOSFET if it has nowhere to go. But since there's this diode here, right, with the anode on this side, that spike does have somewhere to go. It's going to go right up to 12 volts. The negative voltage spike is going to go right down to ground because of this characteristic diode of this MOSFET. So that takes care of that. That's pretty cool. That's why I love using MOSFETs. So that's that. So let's scope this out, and I'm gonna put a probe right here on the switching node, and I'm gonna also put a probe right here on the PWM, and we'll scope it out and see what it looks like. It should look very cool, whatever. So now I'm going to go ahead and, okay, first I'm going to, oh snap, I'm gonna go ahead and kind of, excuse me guys, I'm not a professional YouTuber here. So this yellow channel is going to be probing my input signal, and here is my ground. This channel we're going to probe, so these two, I don't know if you guys can see them, these two little pins here, those two little pins correspond to where my motor goes. Those two pins correspond to basically this node right here, these two nodes right here. And how you see the MOSFETs, these two P channels in the top and two N channels in the bottom, that's exactly how it is right here, where I have this P channel here and an N channel here. Okay, oops, sorry. I have to keep checking my laptop to see if it's focused. Alright, so then this is probing the input signal. This is going to probe that switching node that I mentioned, and then this is going to go also to ground. Hopefully I can get this out of the way. And here, I can back off a little bit now. So here's my motor, and I have it fully not fully anything, just it's just wired up to these little things. I'm gonna go ahead and clip them onto those two nodes. Before I do that, I want to show the motor, I guess, running at the at full speed with no MOSFETs or transistors, so we can see how much current it's gonna draw from my power supply here. So I'm gonna clip this on, and I'm gonna clip this on, and then I'm gonna go ahead and start it, and then I'm gonna show you the screen here of the power supply. Alright, so there it is, running full speed, and at full speed with no transistors, nothing going on, it's running at 12 volts at about almost 1 amp. You guys can see that, that's almost 1 amp. So that's just straight from the power supply. So let's see what kind of performance we can get when we use the whole H-bridge configuration. So again, it's fluctuating between 90 and 89, 890 and 900 milliamps there. So I'm going to go ahead and turn that off, and I'm going to wire it to the circuit and see what kind of performance we get when it's wired to the circuit. Okay, now this, get this mess out of here. Okay, so this right here is these two rails are my 12 volt rail, so I'm going to go ahead and put ground and 12 volts right there. This little rail over here is where my potentiometer is, and this is this rail. Yeah, these two are high, and this is my 3.3 volt rail, which is I'm just using to make a voltage divider. So let's, jeez Louise. Okay, let me first, sorry about the freaking camera, guys. Let me plug in this, holy cow, I just realized I have nowhere to plug in my freaking thing. Let me see if this oscilloscope will power my microcontroller. Well, it seems that it does. Alright, so I didn't have anywhere to plug because my laptop there only has 2 ports, and one is running the camera, the other is running the mic, so I had nowhere to plug in the microcontroller. Alright, so as you can see right now, let me try to make this not such a painful experience for you guys. I'm sorry. One day I will make enough money and get like separate cameras with different angles, and that way I can just switch to a camera. So this is so this is just right now I'm just probing channel 1, which is just the input, right, to the driver. So as you can see, I turned the potentiometer and I'm varying the PWM to the circuit. Now I'm going to turn on channel 2, and that is going to be or at least it should be the that channel now is that switching node of the H bridge, I mean. Alright, so a couple things to notice. If you see that my switching node is actually the opposite of my PWM signal, right? So that's interesting, and I'll tell you why in just a second. So that's at full speed, and then that's completely off. Completely off, and then full speed again. So that's pretty cool. So now let's see how much current the motor is drawing. Now with the that it's in the circuit as opposed to just straight from the power supply. And as you can see, it's drawing just about the same. It's what, 870 or 850, 60, whatever. It's fluctuating, and that's at full load. So the efficiency of this is seems to be pretty good. Operating it through the MOSFETs, I'm not losing that much. So that's pretty cool. So now let's see why these waves are actually inverted like that, right? Because remember, this is my PWM signal from the well, it's from the IC drive, the MOSFET driver, but it's essentially the PWM from my microcontroller because it's a non-inverting driver. And then this is the PWM signal of the node itself, and as you can see, it's inverted. So the reason that is, let's go back over here, and I'm gonna turn this off. It's really loud, and I'm gonna unplug that so nothing is powered on. So the reason it's inverted is because if you look at this, when this node is high, right, this MOSFET is on. When this MOSFET is on, basically it's allowing the current to pass through. So when this MOSFET is on, you can think of it as a short to ground. So when this MOSFET is on, it's like a short to ground. So then you can, pretty much say that this is 0 volts. So when this is 1 or high, this is 0 volts. Now when you turn this MOSFET off, right, you have that sort of negative I don't want to say negative spike, that reverse spike or whatever, and then this MOSFET is still on because I'm not switching this one's just permanently on. Okay, so this MOSFET is permanently on. This motor is like a coil, and a coil is nothing but just wire, so you can kind of think of this as a short, ignoring all the resistance in there. So then this node essentially becomes this voltage. So when this is off, so when this MOSFET is off, this node is at this potential. I hope that makes sense, and I hope I'm not wrong about that either. So yeah, so that's why your signals are inverted like that. Let me see what else. Yeah, I mean that's pretty much it. Obviously, my next step, I think, is going to be to replace all these P channels with N channel FETs. And then from there I have to use a different driver, not this driver, because this just drives a low side MOSFET, and replacing this with an N channel FET has its own issues, which I guess I'll explain when I do my next video. Yeah, that's pretty much it, guys. I was just kind of bored and figured I'd show the new scope working and all this crap. And I'm sorry if this video moves around a lot. Eventually, I would like to have like separate cameras with like an angle here, an angle over there, and all this other crap, and just switch back and forth. That would be pretty neat. Alright, guys, take care of yourselves.